So before going to discuss the boundary layer parameters, I want to tell you one more thing. We will discuss first the boundary layer in case of circular pipes. Okay, so here we are simply discussing the boundary layer for circular pipes. Okay, तो circular pipes के केस में boundary layer कैसे आपके पास work करती है, we'll see that. So let's suppose first I am talking about laminar. Okay, I am talking about laminar flow in pipe. Okay, कि जो pipe में जो flow हो कैसा हमारे पास में laminar flow है. So in this case, let's suppose this is our pipe. Okay, and this is the center line of the pipe. So in this case, when some fluid is going to be enter in the pipe, so obviously that fluid will encounter with the solid surface around this one. Okay, the fluid will have completely around solid surface. In this case means you can say that is the everywhere there is a solid surface. So means as everywhere is the solid surface, in that case we can say that there is boundary layer will start to form from every side of the pipe. Okay, if this is the pipe here, when the fluid is entering here, then boundary will form from every side. Okay, so boundary layer will start to develop from every side of the pipe. So in this case, this is going to be developed like this. Similarly from this side also, from all sides. Okay, and it is going to be merged at the center of the pipe. ये pipe के center पे आपके इसमें merge कर जाएगी. So in this case, first of all, you can say that is for the piping system, the maximum boundary layer thickness that is possible is the pipe radius. So if I am saying if pipe radius is R, okay, so you can say delta max, maximum boundary layer thickness in case of piping system is equals to the R. That is the radius of pipe. But here we have to discuss some points here. So in this case, obviously, we know when the fluid is entering over here, so within this boundary, the flow is having the effect of boundary layer. But in this region, the flow is completely behaving like an non-viscous or inviscid fluid. Okay, because I told you that is beyond the boundary, the behavior of fluid will be completely you can say the fluid will behave like inviscid or non-viscous fluid. So means if I try to draw the boundary at this cross section, if I try to draw the velocity profile at this cross section, so obviously at this point, up to this point, there is a development or there is a velocity gradient. Okay, because this region within the boundary. So up to this point, there is a development of velocity gradient. Okay, because this is within the boundary. But in between here, in this core, okay, this is a core here, actually the conical core type. So in this case, as the fluid is behaving like non-viscous or inviscid fluid, in this case, the velocity gradient is nothing here, almost zero here, and the profile will look like flat here. Okay, so in this case, we are saying this region is inviscid region. Okay, or you can say inviscid flow. But here, this is a viscous flow. In this region, there is a viscous flow. Now, as we move further, in this case, you will see here that if I try to draw the boundary here, or velocity profile here, in that case, up to this point is within the boundary. Okay, this point is within the boundary. So here there is a development or there is a velocity gradient. But beyond this point, in this region or in this inviscid flow core, you can say the curve will be flat. Means now you can clearly say that is beyond this point. Okay, beyond this point, the complete fluid flow is under the influence of boundary layer. Okay, अब पूरा का पूरा fluid flow का आपके पास में क्या हो गया? It is under the influence of boundary layer, and now there is a complete development, and here the profile will look like this one that we earlier discussed in case of Hagen-Poiseuille equations. That is the flow or viscous flow or laminar flow in the circular pipes. So beyond this one, now the fluid is completely under the influence of boundary layer. That's why we are defining this one as fully developed laminar flow. Okay, beyond this point, the profile is set up. Now the profile is not going to change as the pipe diameter is uniform. So in this case, we are saying this is a fully developed laminar flow. And here is the key point, that is the length over which this development will occur. We are defining entrance length. Entrance length. Okay, this is the entrance length in case of a laminar flow. And for this one, we have an empirical relation. Through this one, you can find out this value here. So we are defining entrance length by LE, and the empirical relation you can say. So if we are saying that suppose D is the diameter, if D is the diameter of this pipe, so you can say LE, that is the entrance length, divided by D is given by 0.06 into RED. Here the Reynolds number providing the suffix D means the characteristic dimension in this case is not the length. Here the dimension is pipe diameter. So by this one we will use, and we can find out the entrance length of the pipe in case of laminar flow. This is for the laminar flow. Now if you talk about the turbulent flow, if you take the turbulent flow, in the piping system again. So in this case, if this is our pipe here, okay, this is our pipe here, let's suppose this is the center line here. This, I am defining the section of the pipe here. So again in this case, initially when the fluid will enter here, it is first will behave like in laminar, but suddenly it is going to be convert, or the structure of the flow is going to be convert into the turbulent flow. So in this case, there is a development like this one, then there is a transition zone, and suddenly it will try to switch over here like this. So in this case, I'm doing some transition zone here, it's a little bit bigger. Similarly here, then it's like this one, the transition zone, and suddenly going to switch in this one. So you can see here the development of flow is faster, okay, compared to laminar flow, because in this case the switching to turbulent flow will provide the faster development of flow here. So you can say that is, if we talk about at this point where the turbulent is going to be started, so I told you about laminar sublayer. So obviously at near the boundaries within the turbulent region, there is a laminar sublayer like this. Laminar sublayer like this. Okay, so I'm saying this is laminar sublayer. This is laminar sublayer. Laminar sublayer. Okay, so if we try to draw the development here, okay, if we see the velocity profile here, let me do a little bit this one so you can clearly see here. So in this case, let's suppose if I'm considering this is as a cross section here, okay. So obviously in this case, within the laminar sublayer, the flow character will be like this one. This will be the velocity gradient here, okay, similar here, like this one, within the laminar sublayer. But as I told you, that is in case of turbulent region, the velocity profile is almost flat, okay. So means here the profile will look like this one, okay, the profile will look like this one. So in this case, the behavior here is same within this core and also here, okay. So the profile is almost flat here. So means beyond this point here, in this case, within up to this point, you can say that is here there is a profile like this one within the laminar sublayer, okay, laminar sublayer, the profile is like this one, and then there is almost flat here. So the profile will look like this one, and beyond this point the flow is now fully developed, and we will define this one as fully developed turbulent flow. Turbulent flow, okay, that is our fully developed turbulent flow here, okay. So in this case also, yes, we are having the entrance length here. Okay, this is our entrance length that we are defining by LE. Okay, this is our entrance length. So the formula that we are using for the laminar flow, so for the turbulent flow, that will be LE by D. D again is the diameter of the pipe. This will be 4.4 into RED power 1 by 6. This formula we will use for the turbulent flow here. And one more thing I want to tell you in this case, that is you can clearly see by the diagram, जैसे मैंने diagram draw किया है, the entrance length in case of turbulent flow is less than in case of laminar flow. Okay, जो length होगी आपके पास में entrance length, that will be less than this one. Okay, तो इसके अकॉर्डिंग हम आपके पास में जज कर सकते हैं कि किस तरह से आप सिस्टम को डेवलप करेंगे. तो होता क्या है कई बार एक्सपेरिमेंट्स में, लेट्स सपोज वी वांट टू डिजाइन और वी वांट टू टेस्ट ए मॉडल इन ए विंड टनल. ओके, हमें एक विंड टनल में एक मॉडल टेस्ट करना है, एंड इन दैट विंड टनल वी वांट दैट इज आवर मॉडल मस्ट लाइज इनसाइड द कोर. हम चाहते हैं कि वो कोर के अंदर ही लाइक रहे ताकि उसको फ्रेश फ्लो मिले, उसको आपके इसमें यूनिफॉर्म वेलोसिटी मिलती रहे. So we can easily analyze this one because we don't want that is our model will put inside the boundary layer. So in that case we can easily calculate the values there. Okay, हम निकाल सकते हैं आपके पास में कि in that case what will be the length of the duct. Means let's suppose if this is our wind tunnel here like this one. Okay, this is our wind tunnel, and in this case there are the screens for the purifying the air here. And in this case, let's suppose here is our model, and let's suppose here is the fan we are using, or in this case, so here the air is going to be enter here by when the fan is going to be run here. In that case, the air is going to be enter here like this. Okay, so obviously when the air is going to be hit this boundary here or the solid surface here, there is a development of boundary layer. It will be like this, and we want to calculate what will be the length or entrance length actually of this wind tunnel, so that obviously in this case I am saying that is here in this special case, depending on the Reynolds number, this region or this merging of this boundary will occur beyond this point. So we can easily calculate that is what will be the length of the duct here. Okay, so that our model must lie within this fresh air or out of the boundary region. Okay, so this is how we can easily calculate the length that is required. और आप बोल सकते हैं कि किस लेंथ पे हम अपने मॉडल को पुट करें so that easily okay उसको फ्रेश एयर मिलती रहे और हमारी टेस्टिंग जो आपके पास में वो मेंटेन रहे. So this is how you can explain or you can understand the concept of entrance length in this case. Okay, and there are so much uses of this entrance length in this case. Okay, next we will discuss the boundary layer parameters. Okay, so better है कि आप इसके notes बनाते हो चलिए साथ साथ में. So first parameter that we are discussing here that I already discussed, so I simply tell you what is the first parameter. So the first parameter we are defining is boundary layer thickness, that is delta. So what was the boundary layer thickness? It is the distance normal to the flow direction from the solid surface to the point where the velocity approaches to 99% of free stream velocity, that we are defining the boundary layer thickness. Okay, so ये parameter हम already discuss कर चुके हैं, so इस पर हम अभी focus नहीं करेंगे. So the next parameter that we are discussing is the displacement thickness. Okay, so you can write here the next one is displacement thickness. Displacement thickness. We will represent this one by delta star. Okay, so we will try to understand this one. What is the sense of this term here? Okay, so to understand this one, let's first draw a diagram here. Okay, so let's suppose if I'm saying there is a plate here. Okay, this is a plate here. Okay, this is the plate, and let I'm saying the plate width is B here. Okay, now there is some free stream here, so you can say this is the free stream here. this is the free stream before striking the plate here. So this is the free stream here. Let me draw this one, and it's better that is you also do this diagram side by side. Okay, so this is the free stream here we are defining. So this is the free stream like this. Okay, so obviously it's not going to strike the plate right now at this position, but when it will hit the plate, definitely the velocity gradient will occur here. So right now at this position, this value is u naught. We are defining this value is u naught. That is the velocity here. Everywhere the velocity is u naught here. Okay, so after the strike, okay, after the strike, the boundary layer will start to form here like this. Okay, is it going to be start here like this? So this is the boundary layer formation here, and I will tell you what is the problem when the boundary layer is going to be formed here. Okay, so in this case, this is our boundary layer here like this. So obviously in this case, if I draw the profile of velocity, in that case you can say, let's suppose if I'm considering this is as a cross section here, so over this cross section the velocity profile will look like this one. It will be like this one. Okay, it's gradually increasing up to the approximately you can say 99% of free stream velocity here. So it is gradually increasing. Okay, so it's like this here. So hope कि आप भी diagram draw कर रहे होंगे side by side. I'm drawing this 3D diagram so you can clearly understand the concept of displacement thickness. Okay, so this is our diagram here. So this is how the boundary layer is going to be developed. So now what is the problem and why we need displacement thickness? So before striking the plate, the velocity is u naught, but after striking the plate there is a formation of boundary layer. Okay, so let's suppose at a distance x here, from the leading edge at a distance x here, the total length of the plate that I'm saying this is L here. Okay, let's suppose this is our leading edge here, leading edge here. Okay, so that I'm considering a segment, or you can say a strip here of dy thickness. This is our strip here in this boundary region. Okay, so let I'm marking this B here. Okay, now so obviously the velocity through this strip that is going through this one will be less than u naught. Okay, here the velocity, the local velocity is definitely less than u naught here. So that I'm saying the velocity going through this strip, I'm saying u. So u is the velocity at a height y through the strip dy here. Okay, so can you tell me what will be the mass flow rate that is passing through this strip? Okay, कि strip से जितना mass flow rate आपके पास में होगा वो कितना होना चाहिए? And we are defining this mass flow rate is within the boundary layer. So I'm saying the mass flow rate through the strip. So mass flow through strip. So you can say in this case this is, so you can say rho u b dy. So rho is the density. Okay, so density multiplied by the volume flow rate, you can say the mass flow rate. Okay, density into volume is the mass, density into volume flow rate is the mass flow rate. So here you can say the u is dx by dt. So I'm saying dx, okay, into b into dy. So dx dy into b. So I think this become volume here. Okay, so by dt. So actually u is the you can say this is rate of displacement. Okay, ये आपके इसमें क्या है? It's a velocity. So velocity into area. Okay, so velocity into area. Area is b into dy. So velocity into area become discharge. That is volume flow rate into density. You can say simply what? So this is the mass flow rate that is going through this strip. Okay, and this is happening when plate is present. So plate is present. What is the sense of plate is present? So actually the sense that we are defining the plate is present, it means that is the boundary layer will exist. Okay, so in this case we can say that is this is due to when the boundary layer present. Okay, So this is the mass flowed through the strip when the boundary layer is present. Okay, so what if there is no plate? Okay, if there is no plate, then obviously in that case there is no boundary layer. Okay, so if there is no boundary layer, in that case what will be the velocity that will be going through this strip? इस strip के through कितनी velocity जाएगी? So if obviously if there is no plate, there is no boundary layer, and we are considering the strip is here, in that case the velocity going through the strip is u naught. Obviously in that case there is no boundary layer, no plate, in that case there is no velocity gradient. In that case the velocity will be free stream velocity. So here that velocity that is going through the strip will be u naught. So I'm saying mass flow through strip when no boundary layer. Okay, so in that case the density is rho, that is not going to change, but the velocity will be u naught through the area b dy. So this will be the mass flow rate through the strip when the plate is absent or there is no boundary layer. Okay, so obviously in this case there is some loss of mass due to boundary layer formation. Okay, boundary layer form होने की वजह से कुछ ना कुछ mass loss हुआ है, because अगर आपके पास में boundary layer नहीं होती, in that case the mass was this one, but due to boundary layer the mass is this one, so there is a loss of mass. So you can say the loss of mass through strip due to boundary layer formation. Okay, so you can simply say that is in this case the loss that I'm saying dm, it simply equals to rho u naught b dy minus rho u b dy. Okay, this is the loss here. So in this case you can say this is rho u naught minus u b dy is the loss of mass through the strip due to boundary layer formation. So this much of mass is going to be lost. Okay, ये हमें नहीं मिलने वाला, ठीक है. तो बाउंड्री लेयर की वजह से प्रॉब्लम क्रिएट होगी कि जितना मास मिलना चाहिए था उतना मास हमें मिल नहीं रहा है. Okay, so this is the loss. So if this is the loss through the strip, then what is the total loss due to boundary layer formation? So you can say total loss due to loss of mass, actually loss of mass due to boundary layer formation. So obviously in this case we can integrate the system. Okay, so in this case I'm saying from here to here that I'm saying this is the boundary layer thickness delta here. Okay, so I can integrate this one. So I can say this will be, that is m. Okay, let I'm saying this is m loss हमारे पास में. So we can integrate from 0 to delta, that is rho u naught minus u b dy. This is the total loss of mass. Okay, so this is the problem. Okay, because this is the loss. Now, so I want to overcome this one. Okay, somehow I want to overcome this one, means I need that mass. So if I want to overcome this one, in that case I have a concept that let increase the height, extra height through which we can gain this mass. So means I'm saying that is here I'm assuming there is an extra height here that I can manage. Okay, let's suppose over here exactly extra height over here extra height, and obviously this height is above the boundary layer. Okay, that I'm saying I'm considering this height is delta star. This height is delta star and this is above the boundary layer. So as this is above the boundary layer, so in that case the velocity through this extra height that is going to in here will be simply the free stream velocity. We are not taking approximation, that is 99%. I'm saying here the velocity is going to be u naught here. Okay, so u naught is the velocity that is going through this portion here, that is extra portion that we shifted here. Okay, we are taking the extra here. So here, so I choose the delta star in such a way that is the velocity that is passing through this one is u naught, and so the mass through this portion will be exactly equals to that we lost due to boundary layer formation. Okay, so मैंने exactly इसको इतना शिफ्ट कर दिया है कि वहाँ से जो मास और जा रहा है वो exactly हमें उतना ही मिले जितना कि हमारा मास लॉस हो गया है. एक्चुअली मास लॉस हो क्यों रहा है? यू कैन सी here the profile is like this one, everywhere the velocity is uniform, but here there is a velocity gradient. So in this case this portion we are not receiving, this portion we are not receiving here. So this is providing the loss. That's why I need the extra shift of boundary here. So I am using this delta star. So let write mass flow through delta star. Okay, so let I'm saying this is m here. Okay, so what will be the mass flow through the strip? So rho is the density, u naught is the velocity, delta star is the height, and b is the width. Okay, so this is the mass flow through the delta star, and I told you that is I shifted or I used the height delta star in such a way that is the mass through this extra height will be exactly equal to this one. So means the equation number 1 and equation number 2 are providing the same mass. So actually I am shifting this one, or I am using this one because I want to overcome, okay, or I want to simply compensate the loss of mass. So I want to compensate the loss of mass, that's why I am taking this extra boundary here. So let's equate these two. So by equating these two, you can write this is rho u naught delta star b will be equals to 0 to delta rho u minus u naught, sorry, u naught minus u b dy. Okay, so in this case rho is same here, so rho is out here, this is constant. B is same here, so b is out here. So how much I need of delta star value so that I can exactly compensate the loss of mass? So in this case I can say this delta star, so u naught is going to be here, so this is 0 to delta, this is 1 minus u by u naught, because this u naught is going down here into dy. Okay, and this delta star will be our displacement thickness. So what is the displacement thickness? So it is, displacement thickness is what? It is a distance through which the boundary is going to displace to compensate the loss in mass due to boundary layer formation. Okay, so what is the sense of this one? Delta star is the simply the distance through which we displace the boundary, we choose extra boundary to compensate the loss in mass flow due to the boundary layer formation. Means बाउंड्री लेयर फॉर्म होने की वजह से जितना लॉस हुआ है मास फ्लो का, उसको कंपनसेट करने के लिए जितनी एक्स्ट्रा हमने इसको डिस्प्लेस किया, जितना एक्स्ट्रा हमने लिया आपके पास में, दैट डिस्टेंस और दैट डिस्प्लेसमेंट वी आर डिफाइनिंग डिस्प्लेसमेंट थिकनेस हियर. ओके, सो दिस इज ऑल अबाउट. तो आप ये फॉर्मूला मार्क कर लीजिएगा. सो दिस इज द फॉर्मूला वी आर यूजिंग फॉर द डिस्प्लेसमेंट थिकनेस. क्लियर? सो द नेक्स्ट पैरामीटर वी आर टेकिंग इज द मोमेंटम थिकनेस. So in case of displacement thickness, we defined how we can overcome or compensate our mass. Okay, but in case of momentum, we will try to compensate the momentum. So the definition is like that, that is, it is an amount of distance through which the boundary is displaced to compensate in the loss in momentum due to the boundary layer formation. Means in the last parameter, we try to compensate the mass flow rate, and in this case we will try to compensate the momentum here. Okay, so same diagram I'm using here, and in this case let first I'm saying momentum through the strip when there is boundary layer. Okay, when the boundary layer is here. Okay, so in this case you can say the momentum is simply mass into velocity. Okay, so from here we can say the mass is rho u b dy as we defined earlier, and the velocity is u here. Okay, so here you can say the momentum, so mass into velocity is momentum, so mass into velocity, so this is rho u square b dy is the momentum through the strip when the boundary layer is present. Okay, then we can say momentum through the strip when there is no boundary layer. Means there is no boundary layer in this case. So obviously when the boundary layer is absent here, in that case then we will try to find out the momentum through the strip. But in this case we have to take one precaution here. आपको एक चीज़ का ध्यान रखना है यहाँ पे, that is in this case we will take the same mass, that is rho u b dy. We will take the same mass, but that is moving with the velocity u naught. Okay, mass सेम रखेंगे, velocity क्या होगी, u naught होगी. Why? क्योंकि आप बोल सकते हैं सर इन दिस केस द मास इज गोइंग टू बी रो यू नॉट बी डी वाई विद द वेलोसिटी यू नॉट. ओके, नो, बिकॉज वी ऑलरेडी कंपनसेटेड द मास बिफोर, ओके, हमने मास पहले से आपके पास में कंपनसेट कर लिया है. हियर वी विल ओनली ट्राई टू कंपनसेट द मोमेंटम. दैट्स व्हाई इफ आई एम राइटिंग दिस इज रो यू नॉट बी डिवाइड इनटू यू नॉट, इन दैट केस मीन्स आई एम also including the mass loss. Okay, so no, in this case I only required the momentum loss compensation. Okay, so when the plate is absent or there is no boundary layer, in that case we will take the same mass, that is rho u b dy, okay, moving with the velocity u naught. Okay, same mass moving with the velocity u naught here. So in this case this become rho u naught u b dy. Okay, so now we can find out the loss of momentum, loss of momentum due to boundary layer formation. Okay, so from here we can say this is this term is rho u naught b dy minus rho u square b dy. Okay, so we can say this is rho, you can take u common here, so this is u naught minus u b dy. Okay, so this is the momentum through the strip, or loss of momentum through the strip due to boundary layer formation. So I think again we can find out the total loss of momentum. Okay, so we can find out the total loss of momentum. Okay, so total loss of momentum we can simply find out by integrating this one. So we can integrate this one from 0 to delta. This is rho u naught minus u b dy. This is our equation 1 here. Okay, now we'll do what? We will displace the boundary by an amount theta. Okay, by an amount theta to compensate the loss in momentum. मोमेंटम के लॉस को कंपेंसेट करने के लिए मैंने बाउंड्री को कितना अमाउंट से डिस्प्लेस कर दिया? थीटा अमाउंट से डिस्प्लेस कर दिया. ओके, सो ऑब्वियसली बट नाउ इन दिस केस वी विल टेक, लेट्स सपोज फॉर एग्जांपल, लेट्स सपोज इफ आई एम सेइंग दिस मोमेंटम लॉस इज 10. Okay, now I want to overcome the 10 amount of momentum loss. So in this case I will displace the boundary in such a way that is the momentum passing through this one with the velocity u naught, and obviously having the mass u naught with the velocity u naught, because in this case this is the displacement in the free stream. Here you can't take the same velocity. Okay, but exact amount of momentum that we are taking here, that will be exactly same to the 10 here. Okay, so let I'm saying momentum through theta. So you can say this is rho u naught b dy, sorry, b theta here. This is the mass for it into u naught. Okay, so the theta will adjust in such a fashion that is this total one. Okay, the value is rho u naught square b theta. This will be exact amount of this one. Okay, so यहाँ पे आपको मिस्टेक नहीं करनी है कि आप यहाँ पे भी मास रखें रो यू बी डी वाई. नो नो नो, दिस इज इन द फ्री स्ट्रीम. So here this is rho u naught b theta here, this is this term here. So obviously we can equate the term 1 and 2 and we can find out that is rho u naught square b theta is equals to 0 to delta. This is rho u naught minus u b dy here. So rho is same out, okay, b is same out here. Now theta, so this is u naught square, this going down here. So I'm taking one u naught is out here, one u naught is in here. So in this case this becomes 0 to delta. This is u by u naught 1 minus u by u naught dy. Okay, and this is the formula of momentum thickness. So means by this amount we will displace the boundary through which we can compensate the loss in momentum due to the boundary layer formation. Okay, so this is about the momentum thickness. There is one more parameter that we will discuss here, that is energy thickness. So obviously similar like the mass and momentum, when the boundary layer take place, in that case the energy is also going to be lost. Okay, so the next parameter that we are defining here is the energy loss. Okay, so next one is energy loss, sorry, energy thickness. Okay, and we are defining this term is delta double star. Okay, we are defining this term is delta double star. Okay, so what will be the definition? So in this case the definition is such that is it is the amount through which the boundary is displaced to compensate in loss, to compensate द लॉस इन एनर्जी ड्यू टू बाउंड्री लेयर फॉर्मेशन। ओके, सिमिलर डेफिनेशन है। तो यहाँ पे बस हम बात कर रहे हैं आपके पास में, वी आर सिंपली टॉकिंग अबाउट द कंपनसेशन ऑफ एनर्जी लॉस। ओके, सो विल डू द सेम थिंग हियर। सो फर्स्ट ऑफ ऑल एनर्जी, ENERGY, एनर्जी थ्रू द स्ट्रिप when there is boundary layer, the boundary layer है. So in this case we will take the kinetic energy, that is 1/2 mass into velocity square, 1/2 mv square. Okay, so 1/2 mass is rho u b dy, that is the mass. Velocity is u naught square. Okay, so 1/2 mass into velocity square, that is the kinetic energy. So we can say this is 1/2 rho u cube b dy here. Okay, so this is the energy through the strip when the boundary layer is there. Okay, so energy through the strip when there is no boundary layer, means the plate is absent, there is no plate here. So in that case we can say this is 1/2. Now again, like momentum will take the same mass but with the velocity u naught. Okay, so in this case we will take 1/2 rho u b dy into u naught square. Okay, so in this case this become 1/2 rho u naught square b dy. Okay, so this is the case here. So in this case you can say loss. So loss that I am writing delta E, loss in energy due to, or this is the strip, through strip due to boundary layer formation. Okay, so obviously we will subtract this term from this term here. So this is 1/2 rho u naught square b dy minus 1/2 rho u cube b dy. Okay, there is a loss here. So in this case this term become, I think we can take rho here 1/2, rho here common here. Also we can take the u common here, so u is here. Remaining terms are u naught square minus u square into b dy. Okay, so this is the loss of energy through the strip due to the boundary formation. So the total loss of energy will be, so total loss of energy due to boundary layer formation. बाउंड्री लेयर फॉर्म होने की वजह से आपके इसमें टोटल लॉस कितना हुआ? Again we will simply integrate this term here. So this is integration 0 to delta 1/2 rho u naught square minus u square into b dy here. This is our first equation. Okay, now similarly like the previous case, we will displace the boundary by an amount delta double star in such a way that here the energy passing through this portion will be exactly of same amount of this one. Okay, so we can write energy through delta double star. Okay, तो कितनी होगी आपके इसमें? So again here this is in the free stream, so here the velocity in the mass will be u naught also. So this case will be 1/2 rho u naught b delta double star into u naught square, and this value will be exactly equal to the first term here. Okay, so let me write here. So in this case you can say that we are equating this one, these two terms. So this is 1/2 rho u naught cube b delta double star will be equals to, so this is 0 to delta 1/2 rho u in bracket u naught square minus u square into b dy here. Okay, so from here now we are saying that is 1/2, it's common here out, rho is common here out. Okay, b is common here, is out. Now this is delta double star will be equals to, so the u naught cube, so I am taking one u naught here and u naught square inside here. So this is 0 to delta, this is u by u naught in bracket 1 minus u square by u naught square into dy, and this become our formula for the energy thickness. Okay, so this is how we define the four parameters. First was the displacement thickness, the boundary layer thickness. Second was the displacement thickness. third was the momentum thickness, and fourth is the energy thickness, that is we are defining here like this one. Okay, so ये आपके इसमें तीनों formulas आपको याद होने चाहिए. You have to remember all three formulas. Okay, so this is the formula for energy thickness. So I think this parameter topic is clear to you. Okay.